Friends, today is the Saturday, 8:30 in the Indian Standard Time. So I'd like to welcome you all to this Saturday Manufacturing Talks. Saturday Manufacturing Talks is a mega webinar series, the concerning on advanced topics in the field of the manufacturing. We do have, we have the speakers from different places, universities, industries across the country, across the globe, and we are very fortunate to hear them on different topics like digital manufacturing, industry 4.0, modeling and simulation, and so on. This Saturday Manufacturing Talks is getting organized under through the Center of Excellence in Advanced Manufacturing Technology. This center has been established early 2018 with the support from the Ministry of Heavy Industries and Public Enterprises of India, and forming a consortium of the several industry members. Most of the the times we see that there is no such the link between the industry and the academia. So manufacturing is very much transdisciplinary in nature. So in one hand, we need the presence of different disciplines of engineering. At the same time, the academia and industry must work together. That's the philosophy, that's the purpose, and that's why this Center of Excellence in Advanced Manufacturing Technology has been set up at IIT Kharagpur. And in order to create the awareness of the modern concepts in the minds of the researchers, industry people, academicians, we have come up with this concept of the Saturday Manufacturing Talks. Today, we are very fortunate that the eminent speaker, researcher in the field of the additive manufacturing, who is the Industry 4.0 lead of University of Manchester, Professor Paulo Bartolo is there with us. And we are also very fortunate that Dr. Parthasarathi Mandal is also present. He is also from the same university, University of Manchester, to moderate this session. So I'd like to introduce, Dr. Mandal. Then, as a protocol, Dr. Mandal will take it forward. Dr. Mandal will introduce Professor Paulo, and then followed by that, Professor Paulo will talk about the additive manufacturing, which is a key technology for the Industry 4.0 in the coming days. And after that, question and answer session will be there. Now, I'm so happy today that I got my the best friend, Parthasarathi Mandal, to moderate this this session. Dr. Mandal has graduated from Regional Engineering College, Durgapur. Now it is named as the IIT National Institute of Technology, Durgapur. He's a brilliant boy. He was the topper in 1991 in civil engineering department. Then he has done the MTech from MTech in civil engineering from IIT Kharagpur. So both of us we studied together. And Dr. Mandal is a 10-pointer. So he's a 10 out of 10. He's the topper in MTech. Followed by that, Dr. Mandal has completed his PhD from University of Cambridge in the UK. Now, presently, he is the leader at the University of Manchester. He is working in the field of the structural engineering, bioengineering, and many other interdisciplinary fields. We will have, the joint students, joint research, the publications and all. So I'm very fortunate, very glad. So, Dr. Mandal, so I'm leaving the stage, this forum, in your hands. So please proceed and go ahead. Let us go ahead with this today's seminar.
Thank you, Professor Paul, for these kind introductions and said so many things. Probably I don't fully deserve, but anyway. So it's my pleasure to introduce today's speaker. And as we are chatting, our offices are probably 10 meters apart. But first, before I introduce today's speaker, let me tell a few words about something around today's topics on additive manufacturing as a key technology for Industry 4.0. So Industry 4.0's main thing is the utilization of novel information technology to increase the competitiveness, economic competitiveness through various manufacturing processes. Now, this concept of this fourth industrial revolution is both virtual, for example, Internet of Things, big data, as well as physical environments in the form of autonomous robots and also additive manufacturing. Now, conventional manufacturing probably would not be able to accomplish the necessary mass customizations that is required for Industry 4.0. Now, that's where the additive manufacturing comes in. It has got the capability to create tailored objects with advanced attributes like new materials, shapes, etc. And this technology also offers the ability to produce personalized products with low development cost, shorter lead time, less energy consumed during manufacturing, and as a consequence, less material waste as well. So this on-demand production could even make efficient supply chain and making positive contribution to the environment. So this integration of the cyber and the physical side would create in the near future smart factories with high efficiency that would probably be capable of producing high quality customized products. And also needless to mention, the advancement of IT or information technology is definitely accelerating this industrial revolution. So without much ado, let me introduce today's speaker, Professor Paulo Bartolo. Paulo is a chair professor on advanced manufacturing at the University of Manchester in the United Kingdom. He is the Industry 4.0 academic lead, head of the manufacturing group, member of the Department of Mechanical, Aerospace and Civil Engineering Executive Committee. He is also member of the Advanced Manufacturing Strategic Oversight Group, theme leader of the Industry 5.0 Societal Challenge Area within the Digital Future, and members of the Management Board of the EPSRC and MRC Center for Doctoral Training in Regenerative Medicine. EPSRC in full is Engineering and Physical Science Research Council, and MRC is Medical Research Council. So these are the big research grant, government research grant bodies. Paulo holds a PhD in polymer physics from the University of Reading in UK and had an MSc and first degree in mechanical engineering from the University of Lisbon in Portugal. Paulo authored more than 600 publications in journal papers, book chapters, and conference proceedings. He also co-edited 22 books and holds 16 patents. So without much further introduction, let me hand over to Paulo. It's all over to you, Paulo.
Thank you very much, Dr. Partha. I cannot share. I don't have permissions to share my screen yet.
Ananta, can you give?
I have it. I have it now. Okay. Yeah. Thank you. Thank you very much, Dr. Partha, for your kind introduction. It's always a pleasure to see you through the internet, because as you mentioned, our offices are quite close, but under these current circumstances, we are not seeing each other at university. I would like also to thank Professor Paul for the invitation. It's a great pleasure and a great honor to deliver this presentation. One of my last international trips before COVID was in fact to India, and I had the pleasure to visit IIT Kharagpur, and I hope to be able to visit again your facilities quite soon. As Dr. Partha mentioned, I'm from the University of Manchester, and for those who don't know, Manchester is located at the center of the UK, in between Scotland and London, Edinburgh and London, and it's in a very beautiful area. So around Manchester, we have the Lake District, which is probably 1 hour and a half by car from Manchester, and On the other direction, more or less at the same distance, we have the Peak District. If you like football, Manchester is also the right place to be, because we have two strong teams, Manchester United and Manchester City, and Manchester is well known as a city of sports. And of course, Manchester is also the home of the University of Manchester. It's a top university. We have the largest single university campus in the UK, and as you can see from this figure, the university campus is quite close to the city centre. At University of Manchester, I have several roles, and one is to be the Industry 4.0 academic lead. So this means that I'm interacting with academics from our three different universities, three different faculties, working in multiple aspects related to Industry 4.0. It is also important to mention that for us in Manchester, Industry 4.0 is more than technology. It's also about people. And usually we define Industry 4.0 as a complex social and technical transformation of the world. Of course, that from a technological perspective, Industry 4.0 is about the use of digital tools and technologies, advanced materials, big data, and automation for sustainable and smart factories, products, and organizations. I'm also the head of the manufacturing group, a group of 4 Chairpersons and several readers in lectures and lectures, who are responsible for 2 master programs, one in engineering design, another one in advanced manufacturing technology and system management. And the group is doing research in 3 main domains: innovative manufacturing process, smart manufacturing, and digital manufacturing. All of these domains are enabled by key technologies, which in our case are laser-based process, hybrid manufacturing, additive manufacturing, multi-scale manufacturing, mechatronics, and virtualization. And all of our research is addressing key economic, social, and environmental challenges. Intelligent manufacturing is, of course, a key area. The group is doing research not only in terms of implementation of intelligent manufacturing strategies for industry, but we're also developing tools for smart inspection and predictive maintenance. Human-centric manufacturing is another key area of research. In this case, we are particularly interested in the working environment and improving the working environment from an efficiency perspective, but also from a health and safety. And in that case, we are doing research within the Thomas Aston Institute, a major institute that we have in Manchester, focusing on health and safety aspects. I'm also leading a group of research. This is one of the largest groups in the department. I have 3 research fellows and several PhD students and some master students. And basically, we are using advanced manufacturing technologies, not only additive manufacturing, but also hybrid systems, advanced materials, and molding and simulation for different types of areas of application, mainly for medical, for healthcare, but also for construction, for agriculture, and more recently for textiles. And later today, I'm going to give you some examples about our work in all of these different fields. Well, what is common in all of my activities is additive manufacturing. And as Dr. Partha mentioned, additive manufacturing is a key enabling technology for Industry 4.0 for multiple reasons. So additive manufacturing reduce the complexity of supply chain. Additive manufacturing increase productivity. Additive manufacturing allows to accelerate the development process, reducing time to market. Additive manufacturing reduces the cost of quality. Additive manufacturing reduce inventory. And besides that, additive manufacturing allows a company to implement totally new business models. And I'm going to mention this also during my presentation. Well, additive manufacturing for me is essentially a platform for material design. And at University of Manchester, we have a wide range of commercial machines, but we are also developing our own machines, or to solve some limitations that we identify in existing commercial available systems, or developing machines for specific applications. An example is illustrated in this slide, in the right side of the slide. This is an hybrid machine that we develop. The machine comprises 3 printing heads, 2 pressure-assisted and 1 screw-assisted printing head, and a multi-plasma jet system. So this means that we can print up to 3 different materials per layer. And then we can use the plasma jet system to do surface modification or coating in a selective way. So using this machine, we can create functional graded structures. We can change the surface energy of the materials being printed, again, in a selective way, allowing us to create, for example, self-cleaning structures. We are also developing a wide range of new printing heads. Printing heads combining multiple reservoirs, not only to print multi-material parts, but also to allow us to combine these different materials in different ways during the printing process, enabling the fabrication of functional graded structures. We're also developing coaxial printing heads, as illustrated here. And quite recently, we designed a totally new coaxial printing head with this expanding chamber, which allows to create core shell filaments, very well defined filaments. More examples of systems that we are developing. On the left side, it's a machine that was presented 2 years ago. The concept of the machine was presented 2 years ago during the CRP General Assembly. This was a project with colleagues in Sabancı University, and basically this machine allows to print multi-material filaments. So the critical aspect here is to control the viscosity of these materials, avoiding the materials to be mixed. In terms of additive manufacturing platforms, of course, that we have gantry systems. We are developing also robotic assisted systems, and quite recently we decided to develop mobile robots for additive manufacturing, and we are developing a platform of multiple collaborative mobile robots for additive manufacturing applications. As I mentioned, additive manufacturing for me is a platform for material design, and these allow us to create smart materials using the right type of materials. So again, we have machines, and we are developing also machines to print a wide range of shape-changing materials, which is associated to the concept of 4D printing. So we develop an electrochemical additive manufacturing machine to print shape memory metallic alloys. We are using normal extrusion machines to print also shape memory polymers, so materials that can change the shape based on some changes in the environmental conditions, and these changes can correspond to temperature or to light or to pH, for example. We are also developing a new CAD tool. We call it as an origami CAD system to allow us to design these shape-changing structures. But we are not only focusing on shape-change structures. We're also exploring additive manufacturing to print specific inks, allowing us to create structures that change the color depending on, again, changes on environmental conditions, for example, light. The next slide shows two images of a finger for a prosthetic device, and basically this structure was printed using a shape memory material. As you can see, the material changing the shape upon being heated. So once we immersed in hot water, and then if we immerse in cold water, returning to the original temperature, the structure changes the temperature again, returning to the original configuration. Right now, I have a student developing an artificial arm, which the main idea is to use these shape-changing materials to be sensitive to electrical stimulus produced by the brain. This was, and I always like to include this machine because it was one of the first machines that I developed, or my group developed. This was a machine that I proposed in terms of the concept. I proposed during my PhD, and then once I returned to academia, I was able to develop the system. So the machine, we call it as multi-material stereothermal lithography. It's a VAT photopolymerization system, but in this case, we use a mercury lamp to reduce the price of the machine, and filters to split the wavelength. And we use two different types of light. So we use UV radiation and near-infrared radiation. And the light is used to irradiate a digital micrometer device using optical fibers. In this image, the system has only one DMD, but in fact, the system operates with two DMDs, one for UV radiation and another one for near-infrared radiation. And then we have a reduction lens here to transfer the image created in the DMD into the reservoir. So this reduction lens reduces the image projected on the DMD in 10 times. So if you consider that each DMD has small micrometers of 40 micrometers per 40 micrometers, this means that we can create an image on the surface of the resin of a size of 1.4 micrometers per 1.4 micrometers. Then another new feature that we introduced in the machine was this carousel of VATs, allowing to produce multi-material structures. And in fact, we use this system to propose, and my group was the first group in the world proposing the concept of metallic stereolithography. And to do that, we establish a proper strategy to control the viscosity of the materials being processed by this technology. Well, again, considering additive manufacturing as a platform for material design, due to the unique characteristics of additive manufacturing, and one which is not totally true, but everybody is mentioning that a key characteristic of additive manufacturing is freedom of design. Again, this is not totally true, but nevertheless, additive manufacturing allows us to create very complex shapes that cannot be produced through conventional manufacturing. So because of that, it is now possible to combine topology optimization and additive manufacturing, allowing us to create, for example, very complex lightweight parts, or to redesign existing parts. We are exploring this for multiple areas. An example that I decided to bring today is an example related to medical applications. So, and the case that I'm bringing here is related to the redesign of bone fixation plates. So these plates are made in titanium alloys, or stainless steel. Sometimes can be chromium cobaltum. And the main issue is that they present very high mechanical properties compared to the bone. And as a consequence, we have a phenomenon called stress shielding. And as a consequence of stress shielding, there is some bone loss in the vicinity of the plates. So we use topology optimization. We consider different physiological loading conditions. We impose different volume reductions. And we achieve a couple of designs where it was possible to reduce the equivalent stiffness of the initial plates to a range of values within cortical bone. So we managed to solve the stress shielding problem. Those designs were produced using two different technologies. So we use electron beam and laser-based powder bed fusion. The material was titanium 64, and then we perform an extensive characterization of the plates, including in vitro biological characterization, and we compare the performance of our plates with commercial available plates like Synthesis from Dupuis or Biomet. And we observe that our plates, without any post-processing after being printed, promote a faster interface with the surrounding tissues, as we observe from the very fast cell proliferation on top of our plates. We are preparing a project aiming to assess these plates in vivo, to confirm these preliminary results, which were very promising results. But additive manufacturing has also some limitations that we need to consider when we design a part, and this does not depend on the materials. I'm going to focus more on polymers, of course. And one of the key problems is related to the anisotropy. Anisotropy in additive manufacturing is due to the fabrication strategy, because we are producing parts layer by layer, but it's also to the phase change transformation that the material suffers during the printing process. So in the case of polymers, for example, we start with a material in a solid state, then we heat the material, and the material is then cooled down. And during this process, there is a morphological change, and depending on the cooling process, and also depending on the temperature used to melt the material, all of these conditions affect the crystallization mechanism, crystal size, crystal orientation, and this has an impact on the anisotropy. My group is, or the manufacturing group is focusing on all of these aspects. One colleague from the manufacturing group, Charlie Wong, is focusing on the fabrication aspect using robotic-assisted additive manufacturing and new printing strategies to allowing the user to control the anisotropy, to design the anisotropy, improving the performance, the mechanical performance of the parts. I'm more interested in what's happened in terms of the materials during the printing process. And basically what we are trying to do is to correlate processing conditions with the morphological development, the effect of these processing conditions in terms of the crystallization process, crystal size and crystal orientation, and the effect of it in terms of mechanical properties. 2 years ago, again, we published some papers. So we published also some papers before. And my group was the first group to investigate the in situ morphological development during the printing process using synchrotron. And we start creating models correlating all of these. And we are now designing a new printing head, another totally new printing head, allowing us to control the processing conditions in real time, allowing to design the anisotropy of the final structures. Well, but as you know, Industry 4.0 is about digitization. So it is important to digitize different manufacturing process. And in the case of additive manufacturing, is the same. So it is important to create digital twins of these different additive manufacturing technologies. And again, my group and the manufacturing group is doing lots of research in this area. So we have colleagues, Mike Smith, John Francis, focusing on direct energy deposition. In my group, we are developing digital twins for that photopolymerization process, and the schematic representation of the digital twin architecture and the different elements of the digital twin is illustrated in this slide. But we are also doing the same for extrusion-based process. Right now, the digital twins focus only on the fabrication process. Again, we want to expand the digital twin, allowing to incorporate aspects related to the design, but also related to the inspection and evaluation of the parts being printed, which requires new data analytics and also artificial intelligence engines to allow decision making. But this is an area where the manufacturing group and my group is investing a lot. Now, additive manufacturing, as I mentioned on the beginning, is allowing companies to change their business models. As you know, additive manufacturing allows to produce close to the point of use, and this means that is changing the supply chain. And besides that, because it allows the fabrication closer to the point of use, and also due to the unique characteristics of additive manufacturing, this technology allows a new manufacturing paradigm. We are talking no longer about mass customization, but about mass personalization. And this is a disruptive approach, because through additive manufacturing, the consumers, the users, can be now the creators. So they can be involved in the co-creation process, creating and using their own products. And this is a totally change in terms of the way the products are designed and produced. There are several companies exploring this concept. One is UPS, which is a Proto Labs company, but Shapeways is another example. Usually I call these companies as hubs of 3D printed products, because basically what these companies do is to receive the design from anybody, and they use additive manufacturing systems to create or physically create the designs they receive, and then they ship the product to the designer that will be also the user. In the case of herbs, they have a network of small offices, small companies, or eventually persons using additive manufacturing to produce these products close to the person that submit the design. There are lots of very nice examples of the use of additive manufacturing as part of this mass personalization strategy. Two examples related to personal protective devices are shown in this slide. On the top is an helmet designed by two designers from China, and they designed this helmet using a Voronoi lattice structure, improving the impact absorption of the helmet. And again, this is an example of a design that cannot be produced using conventional technologies. Another example on the bottom is another helmet, in this case for American football, developed by Impressio Tech. And in this case, again, the helmet was designed based on a lattice structure. But besides that, the helmet combines different materials, and one material corresponds to these pillars, and they are made using elastomeric liquid crystals. And basically, the incorporation of these elastomeric liquid crystal pillars improve the energy absorption of the helmet. But there are many other examples. So, for example, a company in Sweden, GasLink, they are creating very complex shape lightning systems, and they are also allowing the users to create their own designs. Designers are exploring the technology to create personalized products. One example is Earl Stewart, which is using additive manufacturing to produce shoes. Or a good friend and colleague is now in Auckland, which is using additive manufacturing to print personalized guitars. And even companies, so I mentioned Shapeways and Herbs, but there are other companies that realize the potential of additive manufacturing for mass personalization. And this covers multiple sectors, including the food sector. Barilla, for example, is exploring additive manufacturing to allow the users, the clients, to create personalized pasta. And this is shown in the video that I'm going to show to you. Well, in our case, we are also trying to change a wide range of sectors through additive manufacturing. And I'm going to give you examples about our work related to 4 different sectors. And the first one is construction. So again, in 2019, we proposed for the first time the concept of construction 4.0. This is quite similar to what you know for industry 4.0. The same goals. The goals are here in the construction sector again to increase safety, to increase productivity, to reduce costs, to transform the sector into a more sustainable sector through a combination of multiple technologies that also promote the communication between the different stakeholders. And this is valid for different types of industrial sectors. So this was what we proposed for construction. Similar to other groups, we are exploring additive manufacturing to print concrete, but we are doing something different. We had an EPSRC project called Rebuild, where the aim was to reuse the material resulting from the demolishing of buildings to create new construction elements. This is a key problem in the UK. Because every year around 50,000 buildings are demolishing, generating more than 400 million tons of waste. So this was one of the main goals of the rebuild process or project. We're also trying to increase sustainability in construction by reducing the amount of concrete being used to create building elements. So, as I mentioned, similar to other groups, we are able to print concrete, but again, we want to do something different. And due to that fact, we developed a digital platform, and this digital platform allow us to design construction elements, minimizing the amount of concrete being used. So basically, in the areas where the construction element is less loaded, we replace concrete by a mixture of concrete with another material. And one of the materials that we are using is cork. We are also using expanded clay, but we are more focusing on cork because it's a very sustainable material with excellent thermal properties. And basically what we can do using this digital platform is illustrated here. So if we start with a construction element, we run a finite element simulation in order to identify areas where, due to the less loading conditions, I can replace concrete by a mixture of concrete and cork. And this is the map of the building element optimized according to our software, where we have areas where concrete was replaced by a composition of concrete and around 30% of cork. 30% was a limitation, mainly because we need to have more expensive pumps. The viscosity, it's a problem here, but we can go to high levels of cork. So to print this kind of structures, it was necessary to create a new printing head, a novel mixing system to mix concrete and cork, and to change the composition in real time during the printing process. This was one of the first structures that we produced. So we start with a composition of concrete and 30% of cork, and by the end we finish the printing process with 100% concrete. And this material change was created in real time without stopping the printing process. So, as I mentioned, this was one of the first structures. So, as you can see, there are some cracks, some pores, and this was essentially due to the lack of process optimization. So we solve most of these problems by optimizing processing conditions. This is another example of another structure. And again, we were able to create a functional graded structure by changing the amount of cork present in the concrete system. Besides reducing the weight of the construction element and reducing the amount of concrete with significant positive environmental impact, this strategy will allow us also to create houses with much better thermal performance. So this image shows that effectively we were able to have a good control over the amount of cork during the printing process. And as I mentioned, these strategies allow us to reduce the energy consumption in a building. We run a simulation program, and basically the idea was to investigate the energy consumption of a room in Manchester and Lisbon into different scenarios. One was considering that all the walls were made with 100% concrete, and the second scenario where we have concrete cork gradient structure. And as you can see, using these functional graded concrete cork building elements, it is possible for a room in Lisbon to reduce the energy consumption in order to keep the temperature in the room more or less constant between 18 degrees and 26 degrees throughout the year. Another area where we are using additive manufacturing for mass personalization is related to healthcare. I'm going to present some examples related to tissue engineering, a kind of creating body spare parts. We are exploring two different strategies. So basically, one is to use additive manufacturing to create what we call it as a scaffold. The scaffold is a kind of mold, so similar to the injection molds that we use to give shape to plastic. We use these scaffolds to give shape to cells. And then we seeded the scaffolds with cells implanted into the body, or we pre-culture in a bioreactor before implanting in the body. A second strategy is based on the use of additive manufacturing to print biowings. These biowings are made with soft materials, hydrogels containing a large amount of water and cells. And the beauty of this strategy is that it allows us to print directly into the body of the patient. And I'm going to show you one example of this being developed by my group. We are exploring different materials depending on the application, and again a wide range of technologies. So not only extrusion-based machines, but also powder bed fusion and hybrid technologies. We are particularly focusing on bone, cartilage, and skin. Few examples, and the first example corresponds to an EPSRC project that we have called Bone Bricks. And this project was inspired after a visit a few years ago to Turkey. I have a good collaboration with Sabancı University, and I visit Istanbul during the war in Syria, and I was impressed with the problem that Turkey was facing due to the Syria refugees crisis. And I discussed with a couple of clinicians, and I realized that from a medical point, this was quite problematic, and a significant number of persons presented very large bone defects. We are talking in some cases of defects around 20 centimeters, highly infected, and the only solution was amputation, with a significant impact on the patient and on the families. So we decided to propose a solution low-cost solution to this problem. And basically, the idea was to develop small structures with a composition and an architecture similar to bone, easily assembled by the clinician. And that's why we call it as bone bricks, small elements that allow the clinician to create a synthetic bone. Of course, that the clinician, they don't know about additive manufacturing. They don't know how to design these structures. So it was necessary to develop all the software to support this. So we developed tools that, based on medical images, these tools automatically generate the shape and the size of these bone bricks, and also the software to control the machine and to print the structures for the clinicians. These are examples of few layers of anatomically designed bricks with different porosities, and we tested these structures in the lab from a mechanical perspective, but also from a biological perspective. And we are right now running preclinical studies. Due to the COVID, it was we were forced to delay everything, but we expect to finish these preclinical studies in sheeps by the end of October. And after that, we are planning to submit another proposal where the plan is to repeat these preclinical studies in large animals and also to start some human trials. To optimize the characteristics of these structures, we are developing different surface modification approaches. A few examples here. So in this case, we use an acetone vapor annealing to induce some microporosity on the scaffolds, and then we dope it with dopamine, the scaffolds, to improve the biological properties. Other strategies involve, for example, coating the scaffolds with nano silica particles, again, improving the biological performance without compromising mechanical properties. We were able also to create biomimetics constructs using extrusion-based machines and a combination of biopolymer, biocompatible and biodegradable polymer with nanohydroxyapatite and multi-wall carbon nanotubes. And after printing, we observed that, first of all, the multi-wall carbon nanotubes were highly aligned according to the printing direction, similar to the collagen molecules in bone, in between a polymeric matrix containing nanohydroxyapatite particles, similar to the hydroxyapatite crystals in bone. So we are able also to reproduce the structure and the composition of bone. To combine, and this is quite critical, to combine good permeability and high cell proliferation, we are also combining different technologies. We are combining extrusion and electrospinning. Initially, and this was published in 3D printing and additive manufacturing, we use a flat collector for the electrospinning. And then we published another paper where we use a rotating drum, which allow us to not only to have a better control on the electrospoon meshes, but also to increase the density of that electro spoon mesh. So good control by combining these two technologies, we were able also to increase the biological performance of the structures. We control the anisotropy also of the cell distribution on the scaffolds. Right now, we are trying to mimic the nature of bone. So bone is a piezoelectric material, but it has also a reverse piezoelectric effect. We are mimicking it by developing electroactive scaffolds and piezoelectric scaffolds. We have done an extensive work regarding electroactive scaffolds using graphene and carbon nanotubes. Sorry for the next image because it shows some animals and some blood. We tested these scaffolds together with the application of external electrical stimulation, and we obtained very promising results, showing that the combination of our scaffolds together with the external electrical stimulation not only stimulate new bone formation in a more organized way, but it was also possible to observe the formation of the vasculature system, which is critical in the case of bone. Finally, in terms of personalized medicine, we are using it to print directly into the bone, and we are focusing on two main tissues. One is skin, and the other one is cartilage. In terms of skin, the concept is represented here. So what we want is to develop a machine that uses a scanning device to scan the body of the patient, identifying damaged areas and the extension of the damaged area. And then through a normal reverse engineering, these data will be used to control the printing system. In our case, we are using two printing heads to print aerogels containing two different cells, and using two different bio-inks in terms of the biological materials that we are incorporated. We spent 3 years to develop our current bio-ink, and this is a pectin-based bio-ink printed through a dual cross-linking process. So initially, we perform an ionic cross-linking with the calcium chloride to slightly increase the viscosity, guaranteeing a good printability. And after printing, we irradiate using UV radiation to complete the polymerization process. We observe on the first trials that after 14 days, cells were alive, were able to create cell-cell networks and to produce their own matrix. And then we increase the complexity, creating a real skin construct. And the results are illustrated here. So this is the histological image of our skin construct, and this is the human skin. And as you can see, the structure is quite similar, not only in terms of cell structure, cell organization. There is no mixture between cells, and also the size of the epidermis is quite close to the thickness of the human epidermis. We are increasing the complexity of these models, no longer focusing on a bilayer model. And we have also a project with the UK Cancer Research, the Cancer Research UK, and basically the aim is to use our skin constructs to print also cancer cells to investigate melanoma. And in the area of skin, we have collaborations with companies. A good example is a work with Matoka. We have a couple of patents focusing on novel wound dressings with improved antibacterial properties. Dr. Partha, if you allow me only 2 minutes more to give you two final examples, and I will not take more than that. So one, and I will be very brief, is related to agriculture. So this is something recent in my group. It's part of a project funded by Bill and Melinda Gates Foundation. And basically the idea is to use additive manufacturing and smart materials also to create a biomimetic replica of a leaf to detect the presence of specific pathogens. And in our case, we are focusing on the yellow rust. The yellow rust is particularly critical in the Arabica Peninsula and also in the North Africa. And better than my explanation, let me show you the next movie, which was part of a small part of a program broadcasted by BBC about advanced technologies for agricultural applications, and they briefly mention our project.
Disease spore. It enters the sensor biologically engineered to mimic the crop Like a kind of fire alarm, the sensor sets off an early alert. They can all be linked up, warning other farmers weeks before any damage is visible. And they can be 3D printed.
Another area that we are starting, and I'm very excited with this area because I never thought about using additive manufacturing for textiles. So there are several examples about the use of additive manufacturing for textiles through different designers. Small examples related to the use of very low-cost additive manufacturing machines to print buttons, or even more complex products. This is a company in Italy that is using additive manufacturing to print ties. But when we look to these clothes, for example, it's quite rigid, not flexible, due to the limitations in terms of materials, essentially. And besides that, all of these proof of concepts, they don't focus on the possibility of anyone, me, Dr. Parter, Professor Paulo, to design our own clothes and using additive manufacturing to produce what we design. So this is what we are going to explore in a new center funded by EPSRC. So on the beginning of last year, and we started in January, last year, the UK Research and Innovation Council approved 5 circular economy centers, and 1 is related to textiles. What we are going to do is illustrated here. So we are going to explore bio-based materials, and one of the materials that we start investigating is bacterial cellulose produced by a partner within this Textile Circularity Center, which is the University of York. And the aim is to develop a machine, an hybrid system, combining additive manufacturing, but also weaving to create these textile products. And by the end of the project, one of our goals is to have a fully integrated platform, allowing any consumer to be able to create their own product, to test the product in a virtual environment, and to be able to print using our manufacturing system. As I mentioned, the project started in January. We are focusing right now on bacterial cellulose. There are multiple possibilities to print bacterial cellulose. One is mixing bacterial cellulose with a biodegradable polymer and print the composite using normal extrusion, or preparing a bio-ink, preparing an ink, a bacterial cellulose ink, and then we can use 2 different routes. One is to print the ink in a coagulation medium, using, for example, ionic liquids, or printing the ink in a solvent for densification, so to increase the mechanical properties, and after that finalize the printing process through a final cross-linking mechanism by using UV radiation, for example. We have done something regarding the first method, so mixing bacterial cellulose with degradable polymers. We use PLA. And despite the properties of both materials, and both of them are shear thinning, we observe some limitations in terms of the amount of bacterial cellulose that it was possible to incorporate. So it was very difficult to reach values higher than 25-30% of bacterial cellulose. And because of that, the final structures are still very rigid, and we want to have something highly flexible. But this is an example of a structure. These are examples of other structures. But again, similar to other sectors, we believe that additive manufacturing will totally transform the textile and the fashion sector. And we want to know more about the potential of additive manufacturing for the sector, listening the designers, listening researchers. And because of that, we decided to launch a special issue entitled Textiles 4.0, Advanced Materials and Processing Technologies. I would like to invite you, if this is an area relevant for you, if you are working in this area, please feel free to submit a paper to this special issue. So I don't have any other examples. Two final notes. One is that designing a product for additive manufacturing is totally different than designing a product for casting or for milling. And the users of additive manufacturing, they must know this. And they must know how to design a product for additive manufacturing. Again, a group of universities and companies established this year in UK a Design for Additive Manufacturing network, where the idea is to focus on standards, the information flow, materials, optimization methods. The network is organizing seminars. These seminars are open to everybody from UK and outside UK. The most recent one was organized 2 weeks ago, focusing on teaching, for example. So this is my first note. The second note is about the potential that we have based on additive manufacturing, and what I think are emerging areas combining additive manufacturing and advanced materials. One is, of course, related to smart materials and smart structures, so structures that can sense the environment and adjust their properties to those changes. Another important area is related to the ability to create graded structures, so structures that change their composition and their properties from one point to another one. And finally, printing multiple materials. A good example is related to printing hydraulics, where we need to combine solid and liquid materials. But we have also challenges, and this is my final slide. Challenges related to the models that we are using to optimize the process, for example, or to predict the properties of the final parts. So right now, those models are predictive models, so based on materials that we know, processed under conditions that we know. We need to develop prescriptive modeling approaches, allowing us to predict the behavior of a part made with a material that we don't know, that we never tried before. We need also to have a better measurement and the inspection techniques. Lots of things have been done in terms of using micro CT and CT for assessing additive manufacturing parts. But again, we have problems related to uncertainty estimation and calibration of the systems. And finally, one problem related to health and safety. So additive manufacturing sometimes is not a very safe system. There are fumes, there are gases released during the printing process. Even low-cost machines able to process ABS, for example, they present health problems, and we need to investigate more the implications of additive manufacturing for health. And with this, I complete my presentation. Thank you again. Thank you, Dr. Partha, for allowing me more time. And thank you, all of you, because, spending 1 hour in a Saturday evening, listening me, you deserve my thanks. Thank you very much.
Thank you, Paulo. I'm sure all the participants are really excited to hear this excellent talk. Means you just showed what additive manufacturing could be. When starting from your initial fiber printing, multi-material fiber printing, to metallic stereolithography, to designing anisotropy, and then personalized healthcare products, including biomaterials like bone and cartilage. I'm definitely looking forward to one of those helmets, that cycling helmets that you can print for me. But nevertheless, it was an excellent talk. Thank you very much, Professor
Thank you.
Bartolo. There are few question and answers people have put in the chat. I'm sure you'd be able to answer some of those. So the first question comes from B.S. Sharma. The question is, medical implants with micropores fabricated using additive manufacturing has better properties with respect to cell growth or the solid metal implants?
No. So what we knew that from the scaffold. So if you control the microporosity, you increase cell adhesion and differentiation. We decided to do the same with our bone fixation plate. So once you printed the structure using electron beam or selective laser melting, the surface presents some roughness. So we decided not to post-process the plates. And when we compare our plates with polished commercial plates, we observe a significant difference. So cells were able to grow in our plates and not able to grow in the commercial plates. And we assume that our plates, once implanted, will create a better tissue interface with the surrounding tissues.
A related question from B.S. Sharma again. How metal foams fabricated using powder metallurgy are compared to with the additive manufacturing?
Sorry, can you, I missed the first.
So the comparison between metal foams if fabricated using powder metallurgy as opposed to the additive manufacturing.
Oh yeah, I don't know. We never compare the use of other technologies. So I know that we can create a metal structure using metal injection molding, and we are able to create a foaming structure, but we never compare the properties. One thing that I can tell you is that with a non-additive manufacturing process, you cannot control the structure of the foam. With additive manufacturing, you can.
Thank you. So there are some questions in the chats as well. Let me get the chat. Just 1 second. Sorry.
In terms of polymers and regarding the other one, we not for medical applications, but for automotive applications, we are using a technology called MuCell. MuCell is an injection molding technology where we use a supercritical fluid to create a foaming structure. What is the difference of a final structure produced using MuCell and an additive manufacturing? In terms of the microcellular structure, is that sometimes we don't have an open pore structure. And this is, for example, is required for medical applications.
Thank you. Next question, Paulo, is it possible to build the scaffolds out of bioresorbable materials?
Yeah, that is a very good question and a topic of debate. So myself and other colleagues, we classify a scaffold as a temporary structure. So based on that definition, the scaffold must be produced using biocompatible and biodegradable materials. Well, the number of metallic materials that are biodegradable are quite limited. We have magnesium, which is difficult to process. We have iron. So it is not common to create a biodegradable metallic scaffold. We can incorporate these materials with polymers. But nevertheless, there are groups that are producing lattice structures made in titanium, and they are calling those structures as scaffolds. I don't agree, but yeah, for me, a scaffold should be a temporary structure. And the role is to provide support to cells, for cells to grow, generate a new tissue, and by the end, the structure will disappear and we'll have a new tissue formed, which is not possible with a non-degradable metallic structure.
Thank you. Next one, I thought someone would ask, I would have, is about the Barilla pasta. So question is, what is the cost versus benefit? It's, for example, retention of the sauce, for example, compared to the other pasta that Italy have been producing over centuries, for example.
Okay. Now, sometimes the cost is not is for the user is not the really issue, because what the user of a machine like that wants is something different. It does not pay too much attention to the price. But of course, that in some cases, mass personalization generates more expensive product, but it's an individualized product. It's a unique product. What people working in the field of additive manufacturing is trying to do, and that's why the concept of mass personalization is to reduce the price of these individualized products to a similar level as the cost of a product being mass produced. But in many cases, this is not possible. In terms of the cost of the pasta, really, I don't know what is when we compare a pasta printed by the Barilla machine or a similar pasta traditionally made, I don't know the difference of the pasta. I'm very sorry. I tried once, but I was not able. There is a restaurant in London, by the way. If you have the chance to visit UK, try to go to that restaurant. So it's a restaurant that is using additive manufacturing to print food. But besides that, they are using also augmented reality. So the idea is not only to print food, is to provide a new environment. And everything apparently in that restaurant is 3D printed. So the table, the chairs, the forks, the knives, everything is 3D printed. But again, don't ask me if it is very expensive or not. I don't know. I tried to go there once. I had a meeting in London. It was not possible, and then I promised to myself, I'm going next week. And then we have the pandemic, and it was not possible to travel. So again, and I don't know if the restaurant will reopen after this. I hope so. So if they will reopen the restaurant, this is my suggestion. Go there and try.
Thank you,
and I
Paulo.
don't have shares on that restaurant, by the way.
There are a couple of questions. One on the bone bricks. Somebody is asking us what was the process involved. I guess they can look at the publication. Can they?
Yeah. But we are using extrusion and screw-assisted extrusion.
Okay, and similarly, the designing the anisotropy, somebody had asked the question. Again, I would ask you to look at Paulo's paper. But one question, probably this is the last question because I'm aware of the time, is that can additive manufacturing be useful for non-Newtonian materials? As such, highly viscous non-Newtonian materials are very important in biomedical and tissue engineering applications.
Yeah, no, that is a good point. I can send to Professor Paulo one paper being prepared by one of my PhD students. So he's developing a new coaxial printing system. So a little bit similar to what I mentioned in the presentation, but this coaxial printing system is linked to a screw-assisted system and a pressure-assisted system. With the screw-assisted system, the idea is to be able to print high viscous materials. The only characteristic that we need to guarantee in extrusion is that the material must present a shear thinning behavior. If not, it will be more difficult to print, or very difficult to print.
Thank you. There are lots of comments in the chat about the thanking you, Paulo, as the excellent talk,
Thank you very
etc.
much.
And looks people have enjoyed. So what I can say, I can summarize with possibly one of the quotes that Arthur C. Clarke once said, it's his famous third law, that sufficiently advanced technology is nothing but magic. And when Paulo joined Manchester University after his talk, I was in that position. I exactly told him that. And he told me that, come here. He took me to his office and he showed me a newspaper cutting. So he came from Portugal just a few days back. And the local Portuguese newspaper wrote exactly the same thing. The magician is gone from Portugal now to UK. So Paulo, that is magic, this advanced manufacturing and the additive manufacturing that you are weaving in Manchester and for the humanity throughout the world. It's magic. Thank you very much.
Thank you. Thank you very much. And
thanks to IIT Kharagpur for giving this opportunity for me to moderate this excellent session. Thank you.
And Professor Paul, thank you very much again for the invitation. Extend my compliments to all your team, to all the participants. You have my email. Feel free to provide my email to all of you, and thank you also to give me the opportunity to see again Dr. Parthasarathi Mandal through this digital media, but it's always good to see him.
Thank you so much. You know, the Paulo, I was just listening throughout your presentation. It is phenomenal. The type of work that you are doing, it's really wonderful. You know, I just got mesmerized by seeing the applications of additive manufacturing in the field of the personalized, you know, the healthcare and many more. I mean, it's really open up, you know, our minds and all. So it's wonderful. Thank you so much for your presence. You know, we are really grateful that you have accepted our invitation. Thank you, Dr. Mandal, for nicely moderating the session. It is our really, we are privileged that you are present today as well. Thank you all participants. I think you have all enjoyed, and you can pass on this information that this video, the webinar is recorded. It will be there in the YouTube as well. So anybody who has missed, you can pass on the information to them. They can also download and watch. Thank you so much. I request Amrit to let us know who would be the speakers for the month of the August. Amrit, please.
Oh, that's good. So at least I know one person there. Yes.
Yeah. The next speakers are Ajay Marsley from Purdue University on August 7th. Then Professor Amrit Chakravarti from IIT Bangalore, the famous speaker in the field of Industry 4.0 on August 14th. Then Professor Derek Seglarek from the University of Warwick Manufacturing Group, WMG, on sensing systems and networks in manufacturing. And then Professor Adrian Gelrich from the University of Waterloo. Professor Gelrich will be talking about the high productivity welding process.
If possible, Professor Paul, send me the link for the next one. It will be great. I don't know if I can, but if I can, yeah. I would love to attend the presentation of Professor Ajay Marshall. Professor Marshall is a good friend, very good friend.
Oh yeah, we have kept. You can join all the webinars using the same link. So it's
Oh, okay. And it will be at the same time?
Yeah, it's at the same time, always at the same time. Every Saturday, 8:30 p.m. in the Indian Standard Time.
Okay, that's good. I will try my best to attend the next one.
Thank you so much. With this, I'd like to, close the session.
Thank you.
Thank you.
Thank you. Bye. Bye-bye.
Bye-bye. Yeah. Have a nice day.